Good morning all. We'll start with the second module of Geotechnical Engineering 1. Now these are the contents: the index properties, sieve analysis. We'll discuss well-graded, poorly graded and gap-graded soils. Then you have a discussion on Stokes law, wherein hydrometry analysis will be discussed, and then we'll touch upon a few numerical problems. We'll have a discussion on the relative density, consistency or adaptive limits of soil, few practical applications and numerical problems. Then we'll have a discussion on the lab test for Atterberg limits. Then we'll move on to Indian Standard Classification of Soils, and as a section 2 of module 1 we'll have a discussion on the permeability of soils, wherein we'll have a discussion on the Darcy's law, the factors affecting the permeability, the practical applications, constant and falling head tests, average permeability of stratified deposit, and again a few numerical problems. Now coming to the index properties of soil. Now the index properties of soil are particle size, plasticity features and relative density. Now why we call these three things, the particle size, the plasticity features and the relative density, as the index properties, is that these are the properties that can be used to index or pinpoint the behavior of soil under different conditions. For example, your textbook or perhaps your notebooks will have an index page at the beginning. So when you take a look at the index page of your textbook or perhaps your notebook, you'll get an idea where you can find a particular portion. For example, if you want to find integration to get the area of a triangle, the index page would tell you that it is included in page number 20. Likewise, the index properties of soil, particle size, plasticity features and relative density will hint you about the behavior of soil under the loading conditions or flow conditions, etc. So indexing is suitable and it's necessary for classification of soil and also for an engineer to get an idea of how the soil will probably behave under the loads. Now the particle size distribution will have to cover two things: sieve analysis and hydrometry analysis. Now like I said, index properties are particle size, plasticity features and relative density, and engineering properties of soil will include compressibility, permeability and shear strength, which will be covered in subsequent modules. We'll start with the first thing here, sieve analysis. So sieve analysis is for us to get the idea of particle size distribution of soil. And plasticity features, we'll discuss the Atterberg limits. Sieve analysis is quite simple. You will have a set of sieves or meshes, to be specific, arranged in the decreasing order of their aperture sizes, and you will allow a certain amount or weight of soil to pass through it, and you measure the weight retained on each sieves. So each sieve will have a certain quantity, or in some cases no quantity at all, of soil, and based on which you will get a distribution of the sizes of the particles in the mass of soil that you have taken initially. So you can use either a Sieve Shaker, which is a mechanical device which will help you to shake the sieves, or perhaps you can also use hand shaking methods as well. The procedure is quite simple. You take around 3 kilograms of soil, arrange the sieves or the meshes in the decreasing order of their size, which means you'll have a coarser one on the top and then you'll have the finer one at the bottom. Now then you can place the soil in the first sieve and cover it, and then you can shake the entire assembly for about 7 minutes. So essentially you will then have to separate each sieves and find the weights retained in each sieve, and also the pan. The pan is the one that you keep at the bottommost point. So you have the coarser sieve at the top, and when you move down you will have finer sieves, and at the bottom you will have a pan. So whatever that has passed through all these sieves will be retained in the pan. So once you have done this mechanical sieve shaking, you can draw a tabular column like this. So the tabular column will have the sieve size, soil weight retained in each sieve, based on which you can find the percentage weight retained, and from the percentage weight retained you can find the cumulative percentage weight retained, and from the cumulative percentage weight retained you can find the percentage finer. Now usually in the laboratories that we have around, we have in practice to use sieve sizes marked here. It's not limited to these things, but for the sake of an example, I have taken 4.75, 2.36, 1.18 millimeters, and below which you have 600, 425, 300, 150, 75 microns, and at the bottom you'll have a pan. So you would usually input around 3 kilograms of soil at the topmost pan, topmost sieve, and then you'll allow it to pass through each sieve using the Sieve Shaker, and based on which you'll get the readings of soil weight retained on each sieves, from which you'll get the percentage finer, from which you'll get the cumulative percentage weight retained, from which you can draw the graph. Now, the graph is called as a gradation curve. A gradation curve is a plot of a particle size on the x-axis, which is taken in the log scale, and percentage finer on the y-axis. It looks like this. You have the particle size, which is in the log axis, and you have the percentage finer, which is in the decimal axis on the y-axis, and it's also called as a particle distribution curve. Gradation curve or particle size distribution curve. Now, based on the shape of the curve that you obtain, you can classify soil to be gap graded soil, which is marked in a blue color font and line here, wherein there's a hump in the curve. So such soils which exhibit a hump in the particle size distribution curve is usually a gap graded soil, in which an intermediate particle would be missing. Now, another term is a well-graded soil. The one that you see in the red color font and the line is a well-graded soil, which you can identify based on the shape. It will probably have a shape which is similar to a flat S. So it means that it contains a good proportion of all the particles of almost all the sizes. So a well-graded soil is preferred in construction industry for example, for pavement or embankment, etc. It can give you a good packing and a better density. Then you have a uniformly graded soil. A uniformly graded soil shows a steep curve in the particle size distribution curve, and it may contain particles of almost the same size. You don't have a proper distribution. Instead, one particular size would be predominantly present in the soil mass that you've taken. So those soil is usually a uniformly graded soil. And like we said, the particle size is marked on the x-axis in the log scale, and the percentage finer is marked on the y-axis in the decimal scale, based on which you have three terms. Number one is the effective size D10. The effective size D10 is a particle size such that 10% of the soil taken is finer than that size. So to get that percentage, to get that effective size D10, what you have to do is you'll have 10% finer here. You draw a line parallel to the x-axis, and it will meet the line, the particle size distribution curve, at a certain point. You drop a perpendicular and you'll get the size. So the size of the particle which corresponds to 10% finer is what we call as the effective size D10, which means that, for example, if the effective size is, let's say, 20 microns, just for the sake of an example, it means that 10% of the soil that you've taken is finer than 20 microns. Now the second term is Uniformity Coefficient, Cu, marked as D60 by D10. So you'll get D60 here and D10 here. So when you take the ratio of these two sizes, D60 by D10, you will get the Uniformity Coefficient. Now again, to get the D60, it's quite simple. You'll have 60% finer here. Draw a line parallel to x-axis, let it meet the curve at this point, drop a perpendicular, and it will meet the x-axis at D60. D10 is already discussed here. So D60 by D10 is called the Uniformity Coefficient. So larger the Uniformity Coefficient, more is the range of the particle. As you can intuitively know from the graph, when you have the difference between the D60 and the D10 greater, it means that you have a very high range of particles. The third is the coefficient of curvature. Cc is equal to D30 square by D60 D10. D30, as you might have probably guessed by now, is nothing but the point that corresponds to 30% finer. D60 and D10 is already discussed. So coefficient of curvature is equal to D30 square by D60 D10. So if the coefficient of curvature falls in between 3 and 1, you can expect the soil to be a well-graded soil. Now, the uses of the particle size distribution curves include to estimate the permeability of soil, or perhaps to estimate the compressibility of the soil, or maybe the prediction of features like frost action, stabilization of soils, etc. So in short, what you fundamentally do is to get an estimate of how the soil would behave under load, or when the flow of water is present, or when you have frost action, or when you are trying to stabilize, etc. So based on the relative distribution, you can classify the soil as well-graded, poorly graded, gap-graded, uniformly graded, etc. And that will help you as an index to estimate or to predict the behavior of soil under various conditions.